Okay, so let's do example 39. This is a very kind of common problem in this chapter, and we did mention a little bit before similar things to this example earlier, but we are going to investigate it in more detail now. So we have a mass M. It is suspended from a cord which is wrapped around the pulley, and the pulley has a mass md. It's like the mass of a disc. Okay, so that's why it's D. And a radius R. We will determine the linear acceleration of the mass M and the angular acceleration of the pulley and the tension in the cord. Okay, so we have, this is going to go down, right? The linear acceleration A, angular acceleration alpha for the disc or the pulley, and also the tension on the rope. On the cord, in the cord. Okay, so mass suspended by a cord wrapped around the pulley is given. This is very similar to what we did in 28.8 to 28.12. And we are going to find a couple things, A, alpha, and T, the tension. So first of all, we assume frictionless pulley, but has a mass, md, so it's not an ideal pulley. Okay, and pulley is in the shape of a disc, solid disc to be more specific. Okay, it's not like a hollow cylinder, it's a solid disc. And for the plans, we are going to, as usual, draw free body diagrams, use Newton's laws, and since we want to find out acceleration, because the energy doesn't really gives us the accelerations, right? So we need to relate it to the acceleration somehow, and the way to do so is Newton's laws. So this is again, there's no numbers, it's a symbolic problem, and we expect lower acceleration than if the pulley was massless, because now the pulley has a mass, has more resistance, right? More inertia, and it's gonna kind of resist the change in motion. So it's gonna make it slower. Then the hanging mass, the suspended mass, is not free falling. For example, for part A, you can say that the acceleration is gonna be less than g because it's not free falling. It's gonna be at a slower rate. You can also see that because of that, quickly if I show the free body diagram on this suspended mass, this is mg and this is tension. Since there is acceleration downward, the downward force is dominant. That means mg is greater than tension, so tension is going to be less than mg to quickly estimate the tension. This is actually part C. I'm going to fix that. Okay, so we are going to see what the equations are, and we can double check our estimations. Okay, so for the solution, again, we usually, so far, I mean, before this rotational motion, we neglected the mass of the pulley, right? We said the pulley is ideal, doesn't have a mass, doesn't have a friction. Now we're just saying it's still frictionless, but there's mass. So it doesn't make a difference, and we will investigate that. So let's start with the free body diagram. So this is for the pulley. The pulley at the center, there is the weight force of the disc, right? D stands for disc or the pulley. And there's also reaction forces, Rx and Ry. They are unknown, so we just making sure that we consider them, but they don't really change our answer because we're dealing with torque. We are saying that x and y axes are shown here, right? We need to, since these are free body diagrams, we need to show our axes. It is better to draw one for each, but we are using the same for both, so it is okay. And on the right side, we have the suspended mass, and you can see that W's are labeled differently. So just W is for the suspended mass, WD is for the disc or the pulley. And the tension forces are the same, so you don't need to label them differently, and I wouldn't really label them differently because they are the same. Now we are going to apply Newton's law. Okay, so for the disc, since it is rotating, we are going to do the second law in rotation form. So we are saying sum of torque equals to moment of inertia times alpha. And since the rotation is counterclockwise, we know that counterclockwise convention is, it is counterclockwise is positive, so we're saying this is positive torque. And the only torque on the pulley is due to the tension, because the other three forces are acting on the pivot point. They don't have any moment arm like R, and they don't have an ability to rotate the object. Okay, so that's what torque is all about. If the force has an ability to rotate the object, then it will create a torque, or it will contribute to torque. But in this case, the only force that does that is the tension. So those are, again, we do show it on the free body diagram, but they don't have necessarily have are causing to rotation, and they don't. Okay, so then that means if you follow this second law in rotation form, the only force that does the torque is the tension. And if you look at the so okay, I made a mistake here. So this rotation is negative because it's not counterclockwise. Counterclockwise positive is the kind of the convention. Okay, so this is clockwise, right? Obviously it's going to be negative, so the torque due to this tension is clockwise and it's going to be negative. So that's why when you write the sum of torque, torque due to tension, just write that, is in the form of the radius or the moment arm, which is from here to there, like this. This is R, so it's going to be RT sine of the angle between these two, which is 90. So it gives you negative, it gives you RT, but since this was clockwise, there's a negative sign. Okay, so it's going to be negative RT. That's what we get this from. Okay. And on the right side, we have I alpha. And what is I? For a disk, we are going back to our table 10.2. Again, that's part C. And we're getting 1/2 mr squared as the inertia. And we're putting that in. M is md. So also going to label it properly because this is a symbolic problem. We need to make sure we don't label it. We don't use M, but md, because M is for the suspended mass. So again, this 1/2 mdr squared is the inertia times alpha. Okay, if you pull tension from this, what you're getting is 1/2, it's negative 1/2 mdr alpha. Okay, so this is the magnitude of the tension, and since alpha is also negative, the tension is gonna will be like positive here. Okay, because alpha is also clockwise. Okay, now we will consider the translation of the small mass. Okay, so we're looking at that suspended mass. Since it is translational motion, now we use the second law in the linear form, sum of F equals to ma, but we are doing this for the y-axis, as we shown the axes before. This motion is only along the y direction. I'm focusing on this free body diagram. This is the direction, and you can see that tension is positive, weight force is negative, and we are going to carry them in here. T minus W, that's equal to may, and you can put this on the other side to get this tension here. And are these tensions the same? And the answer is yes, they are the same, right? And let's just analyze what we have. Do we have everything? So we now have 2 equations but 3 unknowns. Okay, so the tension is unknown, acceleration is unknown, but linear acceleration is unknown, but also the angular acceleration is unknown. So it looks like we have 2 equations, 3 unknowns. It is impossible to solve. We need another equation. And once you see the linear and angular acceleration, you should realize there is a relation between them, right? So we are going to make use of that. Okay, and so we have this string here. So both ends have the same velocity and acceleration. Okay, for the pulley, this is the point where the string leaves the pulley. So that's where the tension starts, right? So you have the radial acceleration and tangential acceleration. So what we have is then AY is, first of all, is the same thing as AT, right? That's the tangential acceleration. They're both negative. And that's going to be equal to R alpha. They're also negative. And acceleration and linear acceleration has a relation with alpha. It is in the form of R alpha. Okay, because remember AT, keep pressing the wrong thing. The tangential acceleration is what? R alpha, right? So AT is AY, and this little r is this radius here. So that is capital R, so you're replacing them. Since the directions point the same direction, that's what we are trying to say here by putting those negatives. It's gonna, at the end of the day, it's gonna be the same direction, and you won't have the negative here, okay? And AT is the rate at which the string accelerates off of the pulley, right? So that's the kind of linear acceleration here. Okay, next, using this equation and the equation we developed, so we have like kind of three equations. This is the first tension, second tension, and the third equation is the acceleration relations. You can get rid of the tensions first, maybe like make the 1 equals to 2 and get that relation, and after that plug that AY in that second equation, so everything will be in terms of alpha, and you can solve for it, and this is the answer you get. Double check if you can get this. If you're not able to get that, please again join us in the Zoom meetings. We can show you how to get that. So just the algebra practice here. And AY, once you get alpha, you can use equation number 3. So this is really saying 1 equals to 2. Those equations are 2, and then put this into 3, or put 3 into these, okay, and then you will get that. And this comes from equation number 3. Then you're going to find out what AY is by substituting alpha with that definition, and then go to equation 1 or 2 to get the tension in this form, okay? But once you get them, make sure it makes sense, right? We said that, for example, if the disk or the pulley has no mass, or if it was very smaller than the suspended mass, then the acceleration, linear acceleration, would be negative g, right? So it doesn't make sense. So if I say that this term goes to 0, do I get negative g? Yes, I do. That makes sense, right? Because it would be a free fall then. And also, if you look at the tension, you should get almost 0, right? There shouldn't be any tension if there was no mass. So maybe you can get those MDs in the parentheses, factor them out, and then you're gonna get those. So you will have here, let me see, T is, so you have MD. Let's just make us a little bit bigger. Let's do this quickly. Gonna make a little bit more room here. Okay, so T is, I'm gonna take MD out. Actually we should do M. Let's see, not D but M. M is bigger than MD, right? So that's what we're saying. So we are looking at the case when M is much bigger than, we're looking at the kind of a limit of the problem, okay? Much bigger than MD. And in that case, we're just gonna write here what tension would be. And I'm gonna take M parentheses. This will be MDG at the bottom. I'm gonna take an M parentheses. This should be MD over M. Plus 2M over M. And okay, so so these M's are gonna go away. We get 2 here, so these M's are gonna go away. And what is this? MD over M. m is much bigger, so this is gonna go to infinity, right? 1 over really big number is gonna go to infinity, and 1 over infinity is gonna go to 0. Okay, so the tension is going to be 0 in that case. So this is a nice way of checking if it makes sense when you don't have any numbers to estimate and then compare. So we just did that for checking this, if this makes sense or not. So we see that the mass of the pulley influences the acceleration of the falling mass and lowers the acceleration specifically, right? And it also lowers the acceleration, angular acceleration, and affects the tension as well. So you can kind of see from the equations, that's kind of the beauty of solving problems with symbols, because you can see specifically what it depends on. But again, if m was much greater than md, so m is the suspended mass and md is the pulley, then the pulley will have a very minor effects, and we kind of use that to make sure that our answers make sense, and we can see that now. For today's class, I'm also going to give you a problem, Indiana Jones problem, but I'm not going to give you the answer. So for Friday, I will also post the answers, video and also PDF form of the answers, the solution. But I want you to give it a try and see if you can solve that problem as well. And today, this is going to be the end of today. In next class, again, I will do that. I will add the video and the PDF of the extra problem, Indiana Jones problem, and we will also start chapter 11, the combined motion.